Imagine if I drop you on the side of a massive steep mountain. I blindfold you and I tell you, find the absolute lowest point of this valley or you fail. How do you do it? You can't look at a map. You can't see the bottom. So, you do the only thing you can. You feel the ground with your foot. If the ground slopes down to the left, you take a step to the left. This is exactly what ChatGPT, Midjourney, and every machine learning model in the world does. In the last series, we defined what error is. That error creates a mathematical mountain. But a neural network has billions of parameters. It is blindfolded in a billion dimensional space. To find the bottom of the error valley, it needs a compass that tells it exactly which way is down. That compass is the gradient, and the tool we use to build that compass is calculus. Today, we are going to code this compass from scratch. And I will show you exactly why trying to train an AI without calculus will literally break your computer's floating point math. Let's move to the lab. We are going to build the simplest error landscape possible, a curve where the loss is just square of the weight. If we take a look at this plot, we are currently sitting high up on the hill at a weight parameter of 3. We want to get to the bottom, which is 0. Why do we care about the slope? Because the slope tells you the angle of the ground beneath your feet. If the slope is a positive number, the hill is going up to your right. If the slope is negative, it's going up to your left. By calculating the slope, the machine knows exactly which direction to step to go down. If you don't know calculus, how would you program a computer to find it? You use basic geometry. You take your current position and add a tiny step forward, measure the difference in height, and divide by that step size. Let's translate this formula into Python. We write a function that mirrors the math perfectly. Let's set our step size h to a reasonable 0.01. The slope is roughly 6.01. The machine knows the hill is steep and it knows which way to step. The problem solved, right? We don't need calculus. But here is the thing. In deep learning, if your step size is too big, the AI might accidentally jump over the valley entirely. So, to be perfectly accurate, an engineer will make h microscopically small. And let's make h extremely tiny, like e power negative 17. Watch what happens to our AI when we run this. The slope is 0. The machine thinks it is standing on perfectly flat ground. It stops walking. The training loop is completely dead. Why did this happen? It's a hardware limitation called floating point precision. A standard 64-bit float can only track about 15 to 17 decimal places. When we add e power negative 17 to the number 3, the computer simply cannot resolve a number that tiny. It rounds the position back to exactly 3.0. When the code subtracts the old height from the new height, it calculates f of 3.0 minus f of 3.0, which becomes 0. This triggers an engineering bug called Catastrophic Cancellation. The numerator becomes exactly 0. Your rise is 0 and your slope is 0. Your AI is broken. This is why calculus isn't just a boring college prerequisite. Calculus is an API for bypassing computer hardware limits. Instead of making the computer physically guess and check, calculus gives us the exact theoretical formula for the slope at any point. For our curve w square, the power rule in calculus tells us the exact slope is simply 2 times the weight. No guessing, no hedge, no division, and no catastrophic cancellation. If we plug our weight of 3 into this formula, the answer is exactly 6. Our original guess of 6.01 was incredibly close. But the calculus formula gives us the perfect exact answer with 0 computational overhead and no server crashes. This exact formula is the derivative, and in machine learning we call it the gradient. If the gradient is positive, you are facing uphill. Take a step back. If the gradient is negative, you are facing downhill. Take a step forward. But exactly how big of a step should you take? If you take a massive leap, you bounce to the other side of the mountain. That requires the learning rate and gradient descent, which we will cover later in this series. And there is an even bigger problem. This was easy because we only had one weight parameter, a 2D graph. What if your model is a large language model with 100 billion parameters? How do you calculate a single compass needle for a 100 billion dimensional universe? That requires an upgrade to our math. We need the gradient vector and partial derivatives. And that is exactly what we are going to code in the next video. If you prefer reading, a link for the detailed companion blog post and the Python notebook used is in the description. If this video helped you understand, hit that like button and consider subscribing to continue decode the complexities of machine learning. I will see you in the next one.